Now we're on example 2 of our maximum area and volume problems, and then this one's going to involve volume. So I want to talk about how do we sketch something that has 3 dimensions. So let's take a look at what's called an ellipsoid. An ellipsoid is just a rotated ellipse that forms a 3-dimensional figure. So we're starting out with the same ellipse that we had before in 2 dimensions. So I'm going to go ahead and sketch that. And how do we make this look like an ellipsoid? Well, if we're rotating it around the x-axis, then what we do is make little circular shapes that kind of give the illusion here of 3 dimensions. So just a curve one direction, and the dotted line represents that's the back, the side that you can't see. Now I can rotate this ellipse either direction. So I'm just going to sketch another one up here. Let's say here's my ellipse, but instead of rotating around the x-axis, I'm rotating it around the y-axis. Well, if I do that, then I'd make my shape look like this. And this looks more like, I would say this one looks more like a football, and this one looks more like a doorknob or a pill or something, but it's rotated the other, or maybe a yo-yo. Some people think it looks more like a yo-yo. Okay, the hyperboloid then is a rotated hyperbola. Like an ellipse, a hyperbola can be rotated 2 different directions. So let's first draw the hyperbola here. We're going to draw it twice and rotate it 2 different ways. So here we have, notice this is a negative x squared plus a y squared, so it's going to open in the y direction. It's going to go, the box will be 3 in the x direction, 2 in the y direction. We'll add the asymptotes and draw the hyperbola. So here we go with the asymptotes. That's a little ragged looking. Okay, I think I'm going to straighten this one out just a little bit. Okay, so there we go. And we'll draw, I'm going to draw it so you can see the, oops, I wanted to make that a different color. So let's make, there is my hyperbola. Okay. Now, one way I could rotate it would be to rotate it around the y-axis. If I do that, I actually have 2 pieces. We can think of this as kind of a dish here, with this being the outside of the dish, and this would be the inside. You're kind of looking down into it, and then down below, this would be kind of like the back side of another dish that's facing downward. So kind of think of this as a bowl-shaped thing facing downward, and this one's facing upward. So here we're seeing just the back of it, and here we're kind of seeing inside of it. Now let's draw it again, only facing the other direction. So going out 3, up 2. So drawing my hyperbola again, asymptotes. And, oh, that one's a little off. Okay, so let me do this one again. There we go. And my hyperbola. And then rotating it. Now, what if I rotated it around the x-axis? Well, then we're going to have it do something like this. And let me get this out of the way. So think of this as kind of a big, I don't know, cone that sort of flares out at the ends like that. Okay. Now it's going to continue on in all, forever. It doesn't just end here. But this is a rotated figure then that has a kind of a core in the middle. If you were to lop this off, if you were to tilt this the other way and lop it off about right here, that's what the nuclear power plant tower looks like. If you go on to calculus, you will be dealing with rotated figures. You'll need to be able to kind of draw them and picture them. So I want you to practice with this. I know it's hard to make them look right, but give it a shot. Okay. Now in example 2, we're going to rotate a paraboloid. So we have a parabola, we want to put a cone inside a paraboloid, which is a rotated parabola. A cone with its vertex at the origin is inscribed in the paraboloid formed by rotating the parabola x equals 4 minus y squared around the x-axis. So I'm going to start with x equals 4 minus y squared, and I'm just going to do a little t-chart here of x and y values, picking some values for y and finding x. So if y was 0, x would be 4. So we got this point right here. If y is 1, x would be 3. Or if y is negative 1, x would be 3. So we have 3, 1, 3, negative 1. If y is 2, x would be 0. Or if y is negative 2, x would be 0. So we have these 2 points as well. So here we have our parabola. Now, if we were to rotate this, it's going to be kind of looking like that. So it's rotated around. I guess I should probably do another one over here. Okay, so this is my paraboloid, and it's rotated, and it continues on, forever. But I'm only interested in the part of it to the right of the y-axis, because I'm looking at a cone with its vertex at the origin. So here's the cone with its vertex at the origin, and the cone is inscribed in the parabola. In other words, the edge of the cone is inside the paraboloid. So kind of thinking of like a sort of a skinny bowl on top of an ice cream cone. And every point on the paraboloid right here, every point on the top of the cone is touching the inside of the paraboloid. So those edges coincide. So this point right here is the point xy. And if I were to move that point, I don't want you to necessarily draw extra ones, but let's say I move this point to the left, then I would have a short and squatty cone that looked like this. If I were to move this point to the right, I would have a really skinny cone that looked like this. Now that's getting really, really crowded in here, so I'm going to delete everything but the red cone now. But that cone can change shape just like the rectangle changed shape, just by scooting x and y to the right or to the left. So in this case, I'm interested in x going somewhere between 0 and 4. If it was all the way at 0, there wouldn't be a cone. It would be totally flat. If it was all the way at 4, there wouldn't be a cone. It would just be one skinny line going this way. Okay, now the volume of a cone is this formula here, and I just want to assure you that I'm not going to ask you to have all of these volume and area formulas memorized. I will provide that, but you need to know how to apply it. So the first thing I'm going to do is look at the radius and the height of the cone in terms of x and y. So the radius of the cone would be this distance right here, and that would be y. And this distance right here would be the height of the cone, and that would be x. So height equals x, radius equals y. So I can rewrite my volume formula in terms of x and y like this. 1/3 pi y squared x. But once again, I want my volume to be in terms of a single variable. And just by convention, we usually use x. So I want to substitute something for y. So I have this parabola formula right here. I have x equals 4 minus y squared. So what I'm going to do is solve this for y. And actually, I'm only going to solve it for y squared because I want to substitute something for y squared anyway. So I could say y squared equals 4 minus x and substitute 4 minus x for the y squared that's in the volume formula. That then would give me volume equals 1/3 pi times 4 minus x times x. Now I could simplify that a little, or I could leave it alone, either one. And now I know that I'm going to put this in my calculator as f of x equals 1/3 pi 4 minus x times x. And I'm going to maximize this particular, and this it turns out to be a parabola because it's just an x squared equation. I'm going to maximize this parabola and find out the maximum area of the cone. So we're ready to type this into the calculator now. So let's go back to the scratch pad, and if you go to Menu, Actions, Delete All, you can delete everything that was there before, and we can put in, I'm going to go ahead and go to Menu, Window Zoom, Zoom Standard to kind of get back to our regular window here, and put in the new equation. So this is 1/3 times pi times, in parentheses, 4 minus x, close, and then times x. Times x. Okay, so enter this. And here is a parabola, okay? Now we don't need very much height. You can see I'm only interested in the values from 0 to 4, and I can change my window setting or not. Here's a quick way to change your window setting you might not know. If you hover your cursor over an empty space on the graph, so I'm going to actually put it up here, and hold down on your click pad until the hand appears, like that, until it grips, you can just shift your graph. So I'm just going to shift it till I'm just seeing this part that I want to see. And I can actually do the same thing with axes, but it's a little harder to do with, I can actually grab my axes, grip till my hand grips, and I can make this bigger if I want to. So just a few things you can do, but you can also change the window settings in the window. So I'm going to do Menu, Analyze Graph, and go to Maximum again. And this time I'm going to have to move my little line to the left, push Enter. You move it to the left of the maximum point, push Enter, then move it to the right of the maximum point till the maximum point appears, and push Enter again. And here I have my result. F of x now represents the volume of the cone, and x represents the x-coordinate, which was the height of the cone. So let's go ahead and sketch this on our paper. So we have this parabola here. The top of the parabola is the point 2, and I think it was 4.19. So we can say when x equals 2, the maximum volume is 4.19 units cubed. So the height of the cone equals 2 units. Y equals the radius. So if I wanted to find the radius of the cone, I would need to look at one of the equations that have x and y in them. So I have two different equations that have x and y. I have the volume equation and I have the equation of the parabola. In this case, it would be much simpler just to use the equation of the parabola. When x is 2, what is y? So I can say 2 equals 4 minus y squared. So y squared, all right, that actually I should have just used this version. Y squared equals 4 minus 2, or 2. So y is the square root of 2. So the y equals the radius is the square root of 2, which is 1.414 units. So now I know that the maximum volume of the cone is 4.19 units squared when the height of the cone is 2 units and the radius of the cone is 1.414, which are the x and y coordinates of this point right here. Okay, so there's an example for volume. Now, just to let you know, on the worksheet, your first worksheet on this concept, the first problem is broken into multiple steps for you, and the complete worked out key, including the calculator work, is shown on the key so that you can check as you go and make sure you're doing the process correctly. And then I think there's 3 other problems that either use volume or area.